Hey, you guys, here we are for your last installment of Chapter 19, Nuclear Chemistry, Sections 7 and 8. Let's first look at the uses of isotopes. Isotopes are used to elucidate mechanisms of reactions. Here's a mechanism of a reaction. A mechanism shows how something happens and in what order. So in this little GIF here, you'll see that the nitrogen comes in with its lone pair, steals a hydrogen, and then another molecule comes in, undergoes a combination reaction, and then another one comes in. So these are mechanisms of building a larger organic molecule. So if you happen to label one of these atoms in the either reactant or product to see where it ends up in the product itself. So that's what labeling is used for in mechanisms. Radiometric dating is used to elucidate the age of objects, such as this mask. This is made of linen, or even minerals. Remember, we used uranium-238. We learned about that, was used to date minerals. Structural determination. You can also use a radioactive atom to label an atom. Your book talks about this reaction in specific, that they didn't really know what the Lewis structure was for S2O32-, but by labeling this sulfur with sulfur 35, it could be determined. And I'll let you guys take a peek at that in your textbook. That helped them understand where the sulfur would go. For studying photosynthesis, tracers were used, which are radioactive isotopes that are used to trace the path of the atoms in a chemical or biological process. So all those different cycles that you learn about in metabolism, like the Krebs cycle and the TCA cycle, all that stuff was elucidated using tracers. Either oxygen 18 to see where the oxygen ends up, carbon 14 to see where the carbons end up and what molecules in those different metabolic pathways. So for your fun sheets 16 and 18, you're being asked questions like, are atoms in crystals motionless, and how smoke detectors work. And these are both applications of uses of isotopes. So let's check out uses of isotopes in medicine. Sodium-24 is used to trace blood flow, and iodine-131 makes sense, is used to probe the thyroid, because if the thyroid is not functioning properly, the iodine won't build up or show up in the thyroid like it should. Technetium-99 is a synthetic element and can be used to help image organs such as the heart, liver, and lungs. Technetium is created when they need it because it's got a pretty short, 66 hours half-life. So you have to create it and use it, otherwise it goes away. See technetium-99 here. M means metastable. And it can give you images like this, which show you where that element concentrated itself. So here's some different isotopes. This is a table out of your book that shows the different isotopes and how they're used in medicine. So it makes sense that things like potassium are used in myocardial, that's your heart, correct? Because potassium, your heart needs potassium to function. Now, this is probably one of the main things, that types of instruments that you've seen, when you think of radioactivity, as a Geiger-Müller counter. And that Geiger counter has a window here. And if you're pointing this window at a sample, and the sample is giving off alpha particles or beta particles, you will get a current running, and like completed, if you will. And when it gets completed, then you'll get like a tick over here, a ticking sound. And the more ticks you have, or more counts you have, that the ticks was kind of an old version of that. Now it's just counts. And there's a little screen here that actually runs a running number of the number of counts. And that tells you the radioactivity of the sample. Let's keep on going with biological effects of radiation. Now, talking about those criticality incidents. A criticality incident was where a sample went critical and of uranium or some sort of radioactive material, in which particles were given off in a burst of radiation. And that burst of radiation a lot of times was neutrons. And those neutrons were given off, and then they just basically shot through whether it was a person or whatever, and then broke bonds and caused ionization to occur, which breaks down the subject. Now, how to measure radiation, a common measurement of radiation is called a Curie. And a Curie is indicative of 3.7 times 10 to the 10th disintegrations per second. You don't really worry about what disintegration it is, what type of disintegration. It's a nuclear disintegration per second. So, of course, if something has a high number of disintegrations per second, it's more radioactive and giving off those particles than something that is low. So, a lot of times, this Curie is a huge measurement. A lot of times, you'll see things giving off in millicuries. A RAD, you might have heard of RADs, radiation absorbed dose. A rad is equal to 1 times 10 to the negative 2 joules per kilogram of material. So if my body absorbed 1 rad, that means I absorbed 0.01 joules per kilogram of material, and that would be per kilogram of me, if you will. So kilogram of man, you could call it. So that's what a rad is. A Roentgen, which is called Roentgen equivalent for man, or a REM, is a rad times this RBE. And this RBE is a factor that is multiplied by the rad for the type of particle that is being absorbed. So if it's a gamma ray, it's a factor of 1. If it's a beta particle, it's a factor of 1. But if it's an alpha particle, it's a factor of 10. Now, what seems odd about this is an alpha particle is a big clunky particle compared to these two. However, what they are talking about is we're talking about ingestion. If somebody ingests an alpha particle, that it would kind of beat them to death from the inside out. But if you are bombarded by alpha particles from the outside, they would just bounce off. So here's my person, it would just bounce off, but not a neutron. Neutrons are much smaller and much higher energy, and they zip right through. So I think that those criticality incidents produce these bursts of neutrons, because remember, a fission reaction makes neutrons, and it rips through everything surrounding it, including the people. So that's what a REM is. So why does radiation do damage? I was just talking about that. It rips through the people and rips through bonds. So if you have proteins in there like this, and then here comes, it rips through and basically breaks them into pieces. And then the body has to either try to put them back together, or it can't put them back together. So for fun sheet question 17, I asked you to look at the Chernobyl disaster and think about the dosage that they got. So this is question 1978 out of your textbook. So, and I think the answer to 1978 is in the answer solutions at the end of your textbook, if you want to look at that. As a result of being exposed during the Chernobyl nuclear accident, this was in 1986, and I put a link on there on your fun sheet, a discussion board for this. The dose of iodine 131 in a person's body is 7.4 millicuries. So what does that mean? I mean, the question I have here is use the relationship of, remember this is first order kinetics for nuclear disintegrations. Use the relationship rate equals gamma, this is lambda n, to calculate the number of iodine atoms n to which this radioactivity, 7.4, corresponds. So pop that 7.4 right here and solve for n. Now, of course, you're going to have to use this half-life. And our relationship of T1/2 is equal to ln of 2, or 0.693 over lambda, to get lambda, and then you can solve it. And there's your Curie again. Now, this last question on the fun sheet I call bringing it all together. And this is a question out of your textbook. Your textbook, I think it's number 104 or something like that. It's based on a true story. In 2006. A KGB agent was murdered in London because he was a Russian who had defected to England, and I don't know the specifics behind that, but he was poisoned with polonium-210. So hopefully by this point in the discussion, or in the fun sheet, you're feeling comfortable with writing balanced nuclear equations. So for A, B, and C here, It's basically writing nuclear equations where polonium is prepared by bombarding bismuth 209 with neutrons. So write that and post it to the discussion board. Look up polonium, see who discovered that and the circumstances surrounding that, and then and then finally write an equation for the decay process of polonium, and showing the alpha particle that it decays, that it shoots out on the product side. So that's kind of straightforward. We've done that since the beginning of this chapter, but as far as energy is concerned, these tiny particles have energy. They have a lot of energy, and many of them are moving close to the speed of light. So remember, we use this equation to determine the energy of a particle or a process. So you're going to do that again to determine the energy of the alpha particle in this instance. So calculate your mass defect for the process in letter C, after you write that equation. And I ask you then to look at letter D, to ask you to calculate the energy of that emitted alpha particle given the masses, because remember, during a process you have reactants going to products, and if a particle is one of these small particles, like an alpha particle, is given off, energy goes with it, and that's where you're going to calculate the energy using E equals mc squared. Now remember, that's for one alpha particle. To continue on with this problem, now once you figure out from part D the energy associated with an alpha particle, so if you eat one polonium atom and one alpha particle is emitted, is that going to hurt too much? No, but it depends on how much you eat. So I ask you to figure out the amount of energy released by 1 microgram of polonium-210. So this is no different than that kind of stoichiometry, right? We have micrograms, and then you can convert that to grams, and then you can convert that to moles, and then you can convert that to an energy, because remember, the energy on letter D previously was in joules per atom, but you can put it in joules per mole. So we could do moles down here, and then we could do atoms, and then we could do joules per atom from the previous problem, letter D, and see what you get. Then I wanted us to look at rads. I mean, what does this mean in rads? This is an energy in joules. So using the idea of a rad, which is equivalent to 0.01 joules per kilogram of irradiated material, think about your energy value you got from part E, and then calculate the number of rads absorbed by this man, assuming he weighs 80 kilograms, or his mass is 80 kilograms. And then what is that exposure in rems? And recall those values to multiply the rad by to get a rem. And there's a table in your textbook that talks about exposure from different things, but also you might want to look up and see what the lethal exposure of REMs and RADs is. And I believe that's in your textbook. On page 883 and 882, it talks about the lethal dosage of REMs and RADs. And that was page 883, so I'll write that right here. Now this is kind of a little aside, you know how I like to make many parts to a problem. I keep on having more questions of myself when I do these things, so of course I like to ask you guys to make you think about things. So for this next one, I don't know if you've heard of an LD50 before, but this is an LD50-30. LD50-30 is the dose of radiation expected to cause death to 50% of an exposed population within 30 days. So given this information that you learned, was the dose fatal? From up here. And now let's talk about how mass is going to affect this. Is this dose fatal to a mouse, and is it fatal to a mammoth or an elephant? I just was, I guess, doing mass, mouse, and mammoth. So see what you can find for that. I look forward to what you put on your discussion